Our next example comes out of section 5.1, graphing sine and cosine functions. So in this example, we're asked to graph a bunch of functions, y equals sine x, y equals 5 sine x, y equals 0.5 sine x, and y equals negative 2 sine x. Hopefully you recognize from way earlier in the course that if you stick a number out in front of a function, what you end up doing is vertically stretching that function. Let's start off with a regular sine graph. Hopefully everybody is pretty decent at drawing y equals sine x. Maximum of 1, minimum of negative 1, a period of 2 pi, and so I start at the origin. It goes up to 1, back down to 0, down to negative 1, and back up to 0, and very roughly drawn with a graph paper, it looks like that, and would do the same thing as I went to the left to negative 2 pi, for example. So there's a regular y equals sine x function. Now, for the sake of saving some space and maybe some time, we'll put y equals 5 sine x on the same graph. Y equals 5 sine x should be, I expect, a vertical stretch by a factor of 5. So every y coordinate will be 5 times as high as it was before. So it might be worth labeling a point like, for example, pi over 2 comma 1, just so I can see what happens to it. 1, 2, 3, 4, 5. I didn't make my graph initially quite big enough, so I'll make it a little larger. This is the same thing as increasing your window settings on your calculator, and you'll find that 0, 0 is still 0, 0. It doesn't matter if you vertically stretch it or not, but the rest of the graph will be 5 times as high, and then back to 0 at the same spot, 5 times as low, back to 0 at the same spot. If you were to label this maximum point here, it's now pi over 2 comma 5, and this point that used to be at negative 1 is now at negative 5. It happened to be at 3 pi over 2, and now it's at negative 5. If you were to label that much for me on a graph, I can see that you've got the period right, you've got the max and the min right, so you've drawn this graph correctly. So let's take a look at, and I think it's worth drawing a separate set of axes just so that I don't make too much of a mess. Y equals 0.5 sine x is going to be a vertical stretch by a factor of 0.5, or by a factor of a half. So this graph is going to be half as tall as the original, which means that its period hasn't changed. It has no reason horizontally to change at all, but it will only go half as high as it used to, so only up to 0.5 and down to negative 0.5. So these points now, pi over 2 comma 0.5 and 3 pi over 2 comma negative 0.5. We were able to do this in color on the board in class, so hopefully you were there for that. If not, these ones are hopefully not too bad to follow. The last one, negative 2 sine x, I'll put down here just so that I can keep them separate, not mess you up too badly. We have two transformations happening here, even though we can draw them at the same time. We have the negative, we also have the 2, and so the negative is going to be a reflection. If we graph y equals negative 2 sine x, we need to reflect about the x-axis. And then we also have a vertical stretch by a factor of 2. Now the good news is both of those transformations are done essentially to the y-coordinate, meaning we multiply every y-coordinate by negative 2. So 0, 0 will stay at 0, 0. All what were positive points before are now negative, so this graph is going to head in a negative direction initially, head down to negative 2, and then go up to positive 2. And so this point that was pi over 2, 1 before is now pi over 2, negative 2. And this point that was at 3 pi over 2, negative 1 is now 3 pi over 2, positive 2. And so it's twice as tall as the original, but also basically turned upside down. You notice I've only bothered to draw one cycle of each of these graphs. Really, that's enough for me to see that you understand what the transformation did. Obviously, follow the directions for any question in your book. If it says draw 2 cycles, or draw this from negative 2 pi to 2 pi, or from 0 to 2 pi, follow those instructions accordingly.